Hello, good morning, everyone. We're going to get started with today with a quick warm-up question. What I first want you to think about is which of the following surfaces do you think has the most friction? So we talked a little bit about friction on Tuesday. We talked a little bit about what it means to have more or less friction. So I just want you to sort of think about which of the following surfaces do you think has the most friction. You might want to think about what it means to have more friction. So we'll just take a couple minutes for you to just quickly, answer the poll, see which one you think has the most friction here. Our goal is we're shooting for 100% participation. As usual, I was able to hit it a couple of times yesterday, so let's see how much participation we can get. So we are currently around half participation, which is pretty good considering only a minute into the class. So let's see if we can think about which of the following surfaces do we think has the most friction. We have a bit of an interesting tie here so far. We won't reveal what people are voting yet. Ooh, we just got a flurry of new answers here. Now we're shaking up the distribution. Let's take another couple of minutes or so to quickly vote on this. We're shooting for 100% participation. We're sitting at about 70% so far, which is pretty good. But let's see if we can hit 100%. Every vote, every poll answer matters. We're currently sitting at right around 80% right now, which is really good. We only need a few more people to hit 100%. We're sitting at about 80% so far. For those of you just joining us, I want you to quickly answer the poll with which of the following surfaces do you think has the most friction? We're at around 18 out of 21 so far. That's really good. I think that's almost 90%. We just need a few more people to answer the poll, and then we will move on with some more friction. We're at 20 out of 21. Can we get one more? Okay, perfect. We are doing really well. So thank you all for those of you who participated. We hit our goal here. We hit 100%. So we have a bit of a spread of answers here. We have some people who think grass, some people who think asphalt, some people who think concrete, and some people who think wood. We will get a chance to analyze and further to explore which of the following surfaces we think has the most friction. So don't worry, you will get a chance to answer your own question later on. Okay, so here's what we're doing today. Our goal today is we're going to use friction to try to qualitatively and quantitatively. In other words, we're going to try to do it mathematically and sort of conceptually and verbally think about how friction affects the motion of objects. So there is a graphic organizer on Canvas here for you to fill out as we go along here. This is just to help you keep your notes, just to help you take notes and have a place to write down where just to give you a chance to write down what your thoughts are as we're going through this. So what we're going to do is we actually did a little bit of an introduction to friction on Tuesday. I'm going to do more of a formal introduction today. We're going to do a little bit more activities, some more exploration, some more hypotheses, some analysis. So we're going to do that today. And if we have time, we're going to keep working on the free body diagram and Newton's second law assignment, which will be due next Monday and Tuesday. Okay, so the first thing I want you to think about, and then if you care to share in the Zoom chat, I'd be very happy to hear. I got a lot of different interesting ideas in second period, so I would love to hear what we have in our period. So the first thing I want you to do is think about what happens if we have a meter stick. So you can use, if you have a meter stick, if you have a ruler, honestly, if you have a ruler, if you have a pen, if you have a pencil, anything works as long as it's, fairly, has some amount of length to it. What I want you to do is I want you to hold it with, imagine holding it with two hands like this, And I want you to think about what happens if you start sliding one hand towards the other. So I'm going to give you a better sense of what I mean here. So what we're going to do today is we're going to look at, so in this case, I have a meter stick right here. I'm going to hold it like this, 2 hands, and I'm going to start sliding one hand towards the other. So what I want you to do is first want you to think about what's going to happen and once I start sliding one hand towards the other. So take a couple of minutes to think about that. And then whenever you're ready, I would love to see what people's ideas are, what people have to share. And then we will actually watch a video on what actually happens when that happens and and I will actually do a little bit of I will actually demo it a little bit too. So take a couple minutes to write what you think is going to happen when you start sliding one hand towards the other below a meter stick. And whenever you're ready, just share your answers in the Zoom chat. You can, I think if you just private message me, I would love to just hear what people think. We got a lot of good answers. We got a lot of good ideas in second period. So I would love to hear what people have to share in our period. Okay, so are we just resting it in our hands or holding it with one hand and sliding with the other? So you're resting it on your hands. You're not really gonna be gripping it. So if I had a ruler here, you're not gonna be gripping it with like a thumb over it. You're just holding it on your hands and then you're gonna slide one hand towards the other. So again, you're not gonna be gripping it with the thumb. You're just going to be holding it on your hands. You're gonna slide one towards the other. So we got some ideas so far. I'm going to give you another minute or two to just quickly write out what you think is going to happen. I would love to, we have a bunch of different responses so far. And I would love to hear what you think. And I will share what people think in a second. Okay. So here's what some people are thinking. So what we're thinking is, so we have one idea where the meter stick, if I slide one towards the other, we have one idea that the meter stick isn't going to move. We have another idea that the meter stick could tip potentially over one side. We have one idea that the meter stick will fall towards the side that had the hand sliding. So we have a few ideas so far. What we're going to do now is we're actually going to look at what actually happens when you start sliding one hand towards the other. So we're going to watch this quick video here. Oh, yeah, hold on. I know I forgot to link the audio to it. It's okay. He's not really talking. He's just really just the audio isn't super important here. We'll just see what happens. So as he's sliding one hand towards the other, what sort of happens is that it sort of like staggers. One hand slides first and the other hand slides, and eventually they'll meet in the middle. And it doesn't matter where he starts because as you go on, it's going to it's almost going to alternate which hand is going to go first, and eventually they're going to meet in the middle. To give you a I'll show you what he's doing, and you'll get to see what I'm doing. Okay, so I have a meter stick here, just like this. So what I'm going to do is our goal here is to slide one hand towards the other. So I'm keeping my left hand stationary. I'm going to slide my right hand towards the middle. As I'm sliding, and right around here, my right hand's getting close to the middle. My right hand actually stops moving. So I want you to notice what my left hand does. My right hand is sliding. Suddenly my right hand stops, and now my left hand is moving and eventually my left hand will stop moving, and then my right hand will start moving again. and it'll sort of stagger. One hand will move, one hand will stick, one hand will move, one hand will stick, the other hand will move, the other hand will stick, and eventually they'll all meet in the middle. And it doesn't really matter where I start. It'll do this. It'll still do the same thing where one will stagger towards the other. Notice how the meter stick doesn't actually tip. It stays perfectly, flat. It's just that it'll sort of like jump over which hand goes at a time, one hand at a time. So what I want you to do now is I want you to try to explain, or not explain, but I want you to try to give a guess as to what you think, why do you think this is happening? So within your groups, within individually, just try to create an explanation for the phenomenon, and whenever you are ready, just share it with me in what you think. We had some really interesting ideas in second period. They had some very intuitive ideas. I would love to hear what we think. We have one idea where it just says something about friction. We have one that just says something about physics. Okay, yes, that is true. It is true. Yes, I know it does something to do with friction. But let's see if we can get some bigger ideas, ideas that are more that show a little bit more detail on what's going on. So let's take a few minutes just to try to think about what's going to happen. So let's see if we can get some more idea on what's going to happen. Why is the meter stick zigzagging? Why can't I just slide one hand all the way towards the other? Why is the meter stick not tipping? So let's see if we can take a couple minutes to try to think about why it's happening. And then when you're ready, I would love to hear what people think. So we had some really interesting ideas in second period. I would love to hear what we have in our period here.
It's with the palms facing upwards, correct?
Yeah, but the palms facing upwards, yeah. So I'm moving one hand at a time, and then eventually it'll sort of alternate hands. And it's not even like I'm not trying to move my left hand. It just sort of I'm focused. My brain is being focused on moving my right hand, but it's sort of like I'm subconsciously moving my left hand in order to keep it moving. I'm not actually telling my left hand to move. It's just sort of moving. So let's get a couple. So we had one person just for physics, one person just for friction. We have another idea where it's something where it's like maybe us humans, we don't like dropping things, so we want to keep it balanced. So it's sort of like a subconscious thing where we don't want to keep it balanced. Or maybe it has something to do with the friction of our hands versus the stick. Yeah, it has something to do with that. Any other? Do we have any other ideas? What's happening? What about my palms? When I did it, my left hand didn't move at all. The left hand was pushing it all the way past my right. What? I guess I think it might depend on how big your object is, or where your hands are starting. So like I have a ruler here, and it still works, right? I'm moving my right hand first, and eventually move my left hand. So it's so I guess it depends. I don't know what you might be using. Maybe if you're using a pencil, I don't know if it'll work with a pencil. It might be too small. I think you use the ruler. That's really interesting. Maybe your ruler. Oh, that's really interesting. That's interesting. Are your hands starting at the edge here? Are your hands starting at the edge? Interesting. Oh, okay. That's really interesting. I don't really. You'll have to tell me what kind of ruler you have. I'm very curious because I tried it with my meter stick. I've tried it with a ruler. So slide it to the right, center on my steady hand. It's a wooden ruler. Okay, that's really interesting. Okay. I don't have plastic rulers. I can't really. But I mean, it works. Maybe I can try with my meter stick only a foot. That's really interesting. I'll have to try with a wooden ruler to see if it works. You'll have to trust me on this. It works with a plastic ruler and a meter stick for me. It might just, I guess the material of it does matter. We'll see. Okay, so something to do with, okay, so someone said I have bad palms. I have nice palms. Okay, don't judge my palms. I think my palms are nice. So my palms have more grip on it. Let's try it with something like, I don't know. So I'm gonna try it with a phone. I have a phone here, and then I have a sticky note here, and I'm going to try it with. Let's see if this works. So I have a phone here. This is pretty smooth. I have a sticky note here. This is pretty smooth. I'm doing it now, and if you see, it's still. I'm only trying to move my right hand, but my left hand will still move. So I don't. So I even if I use something that has less grip than my hands, it still kind of works. So that is an interesting idea. Something about not breaking past the minimum energy to move the object. Static. Ooh, someone's using static friction. That's very interesting. We'll keep thinking that. Something maybe something to do with static friction. When you're applying force in both arms, the friction of the finger that is farthest from the center has the least amount of friction on the stick. So all the force is only enough to overcome the friction on that finger. Then once that finger has enough more friction, it zigzags to the other finger. Oh, okay, that's really interesting. So one idea is that that the amount of friction on my fingers are not constant. It's sort of, and so when one finger gets more friction, it sort of starts shifting the other. That's really interesting as well. That's really interesting. My palms are almost sticky. I usually get pretty clammy palms, but right now my palms are pretty dry. That's a good idea though. I mean, I definitely think that if my palms were more clammy, I think that it would definitely have an impact. But right now my palms are pretty dry. The friction increases on the moving hand as it gets closer to the point in which the stick starts to tilt. Yeah, that's interesting too, right? As I'm getting as my hand gets closer to the middle, the friction increases, and then in order to support the stick, the friction increases. Really interesting. As one hand moves closer to the center, there's more of that stick hanging off that side. Oh, that's also really interesting. Okay, so as one hand moves closer to the center, there's more of the stick hanging off on that side. So the mass of the stick on that side is larger. So gravity has a stronger push. Therefore, friction increases on that part of the stick. So your hand is stopped by the friction. That's really interesting. I don't know, like one hand wants to keep the stick balanced and the other hand shifts all the way to the left, the stick will fall over to the unbalanced weight. So what happens if I mean, like it's not even that like it's just that like I can't even try to tip the ruler. It's actually kind of hard to tip the ruler. It's like it's kind of hard to do it. Maybe when you move one over the other, there's less pressure on the other side from gravity, so there's less friction, which causes the hand to move. Okay, that's another sort of idea, right? As if moving one hand towards the other, it creates less friction, so it causes that hand to move. Or does the balance impact the friction? Once one hand has met the middle, the hand stops moving because there's too much friction due to pressure of the balance. You can't really explain it, but the other side becomes easier to move once your other hand moves to spin. Oh, yeah. So this is sort of going along this idea that like the friction and your hands are sort of changing, and so it becomes easier to move one hand versus the other. The hands alternate moving because as the hand moves, the amount of force on the hand with gravity is increased when the hand moves closer to the center. The weight is less spread out. This makes it harder to move one hand, and the next hand is easier to move. So we have a lot of really good ideas here. I think the idea that a lot of people are sort of honing in on is the idea that your friction is sort of changing. It's not like constant. Your friction is sort of changing, and that it sort of makes it so that it's like alternating. Like one of them is going to be easier than the move to one hand is going to be easier to move than the other, and so your hands are sort of going to alternate. Okay, so I like what we're going with so far. So let's keep this idea of of keeping things moving. So we will examine this ruler towards the end of class. We will get a chance to re-examine our explanations, our hypotheses. Now, what I want you to do is sort of use that same train of thought, and I just want you to. And this is sort of like as a way, another analogy that sort of helps us think about why we're shifting our hands and stuff. So I just want you to think about why is it harder to start a car or is it harder to keep it moving? And why do you think so? So on your graphic organizer, there should be another spot for you to get a chance to jot down what you think here. So this car analogy sort of ties into our ruler analogy. They share a lot of the same ideas. So I just want you to think about, is it harder to start a car or is it harder to keep it moving? Why do you think so? I'll take a minute or two for you to just write it down and share what you think. I might actually have a poll for this. Hold on. Hold on. Give me one second. I think I made a poll for this. I'm trying to remember. Oh, here we go. All right, let's do this. All right, let's get a poll here. And if you have any ideas on why you think it's harder, I would love to hear them as well. So our goal, we hit 100% participation earlier today. Let's see if we can hit it again. So we're at 19. Wow, we're moving quickly. We're already at 23 people. That's really good. We're trying to hit 30. So Let's see if we can get some ideas on whether or not we think it's harder to start a car or do we think it's harder to keep it moving. We have 26 votes so far. Let's see if we can hit 30 votes. We'll take another 20 seconds or so. We already have a few ideas. Some people were willing enough to share with me why they think it's harder to start one or do one or the other. We're at 26 votes so far. Can we get 4 more? And then we will get 27. We just need 3 more people, and then we will be at where we want to be. Okay, so here's some ideas so far. We have one person who's one idea that's like, it's hardest. We think it's hardest to start a car because you have to break through the static friction. So we're using this vocabulary that we learned on Tuesday, static friction. I like your usage of vocabulary there. So we found this new thing about Newton's first law. Good way to reference what we learned previously, Newton's first law. Something to do with the activation energy. Something to do with the activation energy. That's interesting. I'll have to think about that one, activation energy. It's hard to start a car because it must be enough initial force to overcome static friction. So something to do with static friction again. It's hard to stop a car, an object in motion, because they already have a certain velocity or acceleration, which means it requires much more force to completely stop it. Interesting. We think that it's hard to start a car, static friction, Newton's first law. Okay, so we have a lot of ideas so far. So what I really want to hone in on here is this idea of inertia, right? And this inertia is this concept that's, that a lot of people have said it's from Newton's first law. So what is inertia? Let's do a quick recap. So inertia is this property of matter, property of mass that makes it hard to start and stop a car. And then this is because of inertia, right? Objects want to do what they're doing. They do what they do. They don't do what they don't want to do. So an object that is in motion, that is in moving, wants to move, right? It's like a first grader that's running around, right? They want to keep running around, right? They don't want to stop. Or if you are at rest, if you're on a couch, right, you don't really want to get off the couch because you're stuck there. You have inertia. So an object that's at rest, that's not moving, wants to stay not moving, and an object in motion wants to stay in motion. So that's the property of inertia. That's how inertia plays into this. Friction also plays a role in establishing inertia, and this is because friction keeps an object from moving. So in order to move an object, you have to overcome the friction. That kind of friction is called static friction, as we learned previously. And additionally, friction also works to slow down objects in motion. Right? So that's called kinetic friction, as we learned previously. So what friction sort of really, like how it sort of works is that friction is really, it's a reaction force. So Newton's third law, if you remember, it says something to do with if you have an action, you have an equal and opposite reaction. So with friction, when you are moving an object on a surface, right, that object is placing a force onto the surface. And so that surface is going to want to react to the object moving on it. And that reaction is called a friction. So when an object moves forward on a surface, the surface is want to push back on the object. And so that reaction force is called the friction force. So the way this reaction force goes, this friction force goes, is it opposes the motion of the object. So if the object is moving to the right, the friction force is going to be moving towards the left. What I want you to think about is, what do you think determines the amount of friction force an object feels? And what do you think, what would you need to know in order to figure out how much friction force an object feels? So take a few minutes to try to think about what you think determines the amount of friction force an object feels. Is it constant? Do all objects have the same friction force? Does it matter where you are? Does it matter how fast you're moving? What do you think determines the amount of friction force an object feels? Take another 2 or 3 minutes. So take as much time to see if you can process your knowledge, see if you can think about what you think determines the amount of friction force an object feels. What would you need to know? We have one idea where it's something to do with the size. So what do you mean by the size? Do you mean like the height, the length, the width, the mass, the weight, the density, so what do you think? What do you mean by the size? There's a lot of things that can impact. So there's a lot of something to do with the surface area. Interesting. Surface area. That's surface area. Something based on the weight and acceleration, the speed at which you're moving, and the material of the surface. Interesting as well. Weight and acceleration, mass, and whether or not it's a motion. Interesting. If you're sort of unsure of what this question is asking, you might want to think about, right, like if I'm driving, what kind of surfaces have more or less friction, right? You know what they say, like, why is it safer to drive on wet roads versus dry roads? Like, why might it be safer or less safe, right? What do you think helps make that term determination? Is it what surfaces are easier to slide on? So that partially can might give you some ideas on what you think might determine the amount of friction force an object feels. I think that the weight and speed and surface area at which the object is moving impact the amount of friction force. So I'm thinking of the example of rubbing two sticks together to make a fire. The faster you move them, the faster they start to smoke. That is really interesting. Right? As you're rubbing when you rub two sticks together, you're creating a lot of friction, and that friction creates a lot of smoke, and eventually it creates a fire. Really interesting. The amount of friction the force the object feels depends on how much force was applied to the object. I feel like force and friction might almost be directly proportional. Interesting. Ice has no friction. Ooh, interesting. Force applied on object, which is the weight and the surface area. Okay, so we have some ideas so far. I like where we're going. So let's see if we can analyze, let's see if we can learn about what we think determines the amount of friction force an object feels. So there are two main things that affect the friction force on an object. Now, there are, again, most of you are saying, there are a lot more variables to this. However, those variables can be a lot more complicated, and so we're not going to quite analyze them in the scope of this class. But I want you to know, for those of you who said stuff like surface area, who said like speed, like that 100% does matter. But just within the context of this class, we're just going to focus on two things, which is the mass of the object and the type of the surface. Those are the two things that we're going to examine in this class that have the most impact on how much friction an object feels. Okay, so why does mass have why do more massive objects have more friction? Well, more massive objects, they exert more force onto the ground. And because of gravity, right? If you're a more massive object, you're going to push on the ground more. And because when you push on the ground is going to push onto you. This means that the ground will essentially have more grip onto you, right? If you're like a little post-it note on like a ground, right? A post-it note is so light that it's like that the amount of force the ground is pushing on it is like, it's like very little, right? It's like almost like the ground is barely touching it. However, like a semi-truck, right? Because it's so massive, it's really digging into the ground, as the ground is really digging into the semi-truck, and so there's a lot more contact essentially between the ground and the surface, which means that that contact force is called the normal force, right? So the normal force is going to be bigger, and so the ground is pushing more onto the object, it's going to resist changes in motion more heavily. So like a post-it note, right? Because it's so light, it has so little mass, the ground is barely going to resist its motion because the ground is like barely touching, it's barely gripping it. And what also determines how much grip an object, a surface has, in other words, how much friction a surface has, is the type of the surface. So different surfaces have different amounts of friction. So as one person said, ice has very little friction, right? You can slide on ice like forever. It's super easy to slide on ice. If you ever tried sliding on asphalt, if you have a pair of shoes that you just want to ruin, you can try sliding your shoes on asphalt, right? Last time I checked, you don't really go very far. And that's because asphalt has a lot more friction than ice, right? And so different surfaces will have different amounts of friction. Like wet surfaces have less friction than dry surfaces. The temperature can also affect how much friction a surface has. So there's a lot of things that can impact the amount of friction a surface has. What I want you to think about now is, why do you think some surfaces have different frictions than others? And if you have any ideas on how you test it, I would love to hear it as well. So why do we think surfaces have different frictions? Why does ice have a different friction than asphalt? Like, I don't know, they're both stuff. So why would ice have different friction than asphalt? Why would asphalt have more or less friction than wet asphalt, right? It's both asphalt. Why would it have more or less friction? What do you think determines how much friction a surface has? So we know that how much friction an object feels depends on what the surface is. So what about a surface determines how much friction it might have? What do we think determines how much friction a surface has? And the idea and the question, how would you test this, is also really interesting, because how you find out how much friction a surface has is through testing it. And so if you have any ideas on how you could potentially test the friction on a surface, I would love to hear them as well. Because surfaces do have different frictions, right? But we don't really know how much friction a surface has unless we test it. And so, does anyone have any ideas on how we might test how much friction a surface has? Do we just like guess it? Is there what's the process behind that? So I would love to hear it. We have a few ideas so far. So rough surfaces have more friction than smooth surfaces. Interesting. Interesting. They have different qualities. Yep. Google it. Yes, you can Google it. Okay, you can Google how much friction a surface has. Okay, but someone has to test it in order to give you the data to Google it. So let's imagine that we lived in, I don't know, 2000. Let's imagine that we were back in the day when I was in high school, when Google didn't exist when I was in high school, because that's definitely what happened. So how would you figure out how much friction a surface has, right? So without Google. You could test it by, no, impossible. No, it is possible. It is possible. It is possible. I believe that. Okay, so you could test it by having two different surfaces, but keep everything else the same. Different IMFs, different less grip, smoothness, use the same amount of force to push something, let go on surface to see how far it goes. Really interesting as well. I don't know how to come up with an actual scientific formula for this kind of experiment. It's just a feeling. Interesting. Okay. Yeah, no, at least, the more porous or uneven the surface is, the more friction there is. We can test it by comparing the surface of a wheel to the ground to see how different they are. Smoothness, roughness, viscosity is all kind of relative. Okay, so I like where we're thinking on this. Pull a standard object on like a motor or something, and then pull it across a surface. These are all some really these are all some really good ideas. And I'm going to tell you right now, that is actually how engineers and scientists actually determine how much friction a surface has. So how much friction a surface has, it's really just a ratio of how much of the friction force to the normal force. And so we learned a little bit about these coefficients of friction, and these coefficients of frictions determine how much friction a surface has, right? And these coefficients are determined by how much, it's like a ratio of the normal force, the upward force of the ground, to the friction force that an object feels. So how much friction? So what determines how much friction a surface has? It's the main thing that sort of determines how much friction a surface has is how smooth the surface is, right? So the smoother the surface, so something like ice, in other words, the less bumps and divots and cracks and stuff like that, the less stuff there is to slow down to resist an object's change in motion, right? Whereas the bumpier the surface, right, the more grip the surface has to slow down an object. So if you have a really smooth surface, right, it's not going to have a lot of grip on a object. But if you have a really bumpy surface, it's going to have more grip, and so it's going to have more friction. And so To show how much friction an object has, scientists and engineers, we use something called a coefficient of friction, which we learned about previously. These coefficients of friction are measured based pretty much by applying a force on an object and measuring the friction force on different surfaces. And then when you measure that friction force and you find the ratio of the friction force to the normal force, that is how you determine the coefficient of friction. So as we talked about previously, there are two main types of friction. There's kinetic friction and then there's static friction. Kinetic friction is how much friction an object exerts on a moving object. This is the friction that you're probably familiar with. So like usually when you're thinking about like friction is slowing me down, friction is slowing a car down, you're usually thinking about the friction on a moving object. However, we also learned about this other kind of friction called the static friction, which is the friction that exerts, that is an object is that a surface, I should say a surface exerts on a stationary object to prevent it from moving. So if I want to move an object from rest, I need to apply enough force to overcome that static friction. Once you apply enough force, there is no more static friction on it. Once it starts moving, there's no more static friction on it, and then the kinetic friction takes over. So it's sort of like you have one and not the other, and when you get rid of one, you now have the other friction. So what is this thing called kinetic friction? So kinetic friction is the friction that a surface applies to a moving object, which means that if an object is stationary, the kinetic friction is zero. So if you want to figure out how much kinetic friction an object is feeling, right, you're going to use this equation here. The force of friction, the force of kinetic friction on an object is the coefficient of kinetic friction. This is something we called mu. So that coefficient is called mu, mu. It's a Greek symbol, mu. And the subscript k, the little k, that tells us it's a coefficient of kinetic friction. So it's a constant that depends on the surface of the object. And so the force of friction an object feels, kinetic friction, is the coefficient of kinetic friction times the normal force of an object. Once again, the normal force of an object is how much force the surface is applying on the object in order to support it. And this kinetic friction force opposes the motion of the object. In this picture here, the object is moving to the right, so the kinetic friction is going to push it to the left. So while there is kinetic friction, which is friction that is moving, there is also static friction, which is the friction that is applied to an object that is not moving. So the friction of static friction is friction induced by the surface to prevent an object from moving. Once the object is moving, there is no more static friction. So kinetic friction, if it's stationary, there's no kinetic friction. If an object is moving, there's no more static friction. So when you're examining, when you're trying to calculate how much friction an object has, you really should think about, is it moving or is it not moving? And then you only work with that type of friction. You will never have to deal with both frictions at the same time. Only one friction applies to one scenario, another friction applies to another scenario. Oh, sorry, I don't know why I said to calculate the kinetic friction. They should actually say to calculate the static friction. So to calculate the static friction, we can use the equation here. This equation looks very similar to the kinetic friction. The static friction is equal to the coefficient of static friction times, which is the mu s times the normal force. The notation here is n. We usually use Fn, so capital F subscript n. In this particular picture here, it's n, but it means the same thing. So I think what's a little bit different here is instead of an equal sign, there is a less than or equal sign. This is actually more correct than what I told you previously. The reason why is that the static friction force, this is the maximum friction force an object can apply to keep something object stationary. So if you barely touch an object, right, there's only going to be a little bit of static friction needed to resist it. If you apply a lot of force, there's going to be more static friction available to resist it. However, there is a maximum amount of static force that an object can have, and the maximum is mu, the coefficient of static friction times the normal force. The reason why it's a less than or equal is because let's say hypothetically you barely touched an object, right? That object, if that object is not going to suddenly move backwards, right? It's going to stay stationary. So, and if you push it a little bit stronger, right, the object is still it's going to have a little bit more static friction, but it's still going to stay stationary. That static friction force is never going to physically push your object backwards, right? So because of this, your static friction can never exceed the amount of friction you apply until you reach the sort of the cap. Once you sort of hit the max of the static friction, then it can't apply any more friction, and in which case it switches over to kinetic friction. So you should think about basically, am I applying enough force to overcome the static friction? If I'm not applying enough force, then the static friction is equal to my applied force. Once I apply enough force, then the static friction is going to be 0, and then I switch over to kinetic friction. So that's like the main difference here. Static friction is sort of like a variable. It can sort of change. But once you apply enough enough applied force, then your static friction can't keep up, and it just becomes 0. So let's sort of recap what these coefficients mean. Mu, okay, the coefficient of kinetic friction, and mu s, coefficient of static friction. So these are the coefficients of kinetic and static frictions for different surfaces. So again, they will vary between surfaces. And the two coefficients for the same surface will also be different from each other, right? For the same surface, you're going to have a different coefficient of static friction than a coefficient of kinetic friction. Usually your coefficient of kinetic friction is less than your coefficient of static friction. And that's because it's easier, you have less friction force on a moving object than a stationary object because it's easier to resist. It's easier to keep an object moving than it is to make an object move. What this sort of means is that once you apply enough, which means that you don't actually have to, once you overcome the amount of static friction an object feels, you don't actually have to, you can actually reduce the amount of force you have because you don't actually need to apply that same amount of force in order to keep it moving. You only need to apply that much force to start it moving. So that's something that's also kind of interesting. So again, these are just these coefficients, they're just numbers. They don't even have any units. They just tell us how much friction a particular surface has. So they will differ from surface to surface. For example, ice has a coefficient of static friction of 0.05, whereas asphalt has a coefficient of static friction of 0.7. So asphalt has much more friction than ice, which makes sense. It's a lot harder to move an object on static friction than on asphalt than it is to move an object on ice. And then these coefficients, they're just basically just ratios that just determine the ratio of the frictional force on a surface to the normal force on an object. So what we're going to do now is we are going to do a quick practice problem. So we're going to take maybe 5 minutes or so to work through a practice problem here. In this particular practice problem, there is a refrigerator with a mass of 1,000 kilograms that is at rest on asphalt. Now, asphalt has a coefficient of static friction. In this example, it is a coefficient of static friction of 0.9, mu s is 0.9, and has a coefficient of kinetic friction of 0.7. So what I want you to find out is what is the minimum amount of force you must apply in order to move the refrigerator. And I want you to draw a free body diagram for this scenario. And then once you've applied the minimum force, the refrigerator is now moving. What is the acceleration of the refrigerator? So let's take a few minutes to work this out. And then once we've taken a few minutes, I will work through it on the board to try to let's take about 1 more minute, and then I will work through it on the board. Okay, so So what I'm going to do is I'm going to draw two free body diagrams, one for when it's moving and one for when it's not moving. So when it's not moving, right, you have force of gravity pulling it down. Let's think to ourselves, is our is our refrigerator accelerating up or down? No. So which means, and it's on a surface, so there's a normal force applied to it, it's equal and opposite. Rich? Okay, so I didn't give you a direction that you're moving it, but in this case, it doesn't really matter. So what I'm going to say is that there's a static friction force here, pushing against it, and we want to apply a force to make it move. Now, the minimum force we need to apply is equal to the static friction force. So which is why I drew the arrows to be the same size. So we're basically looking for the criteria where the applied force is greater than or equal to the max. I should actually say max static friction. So what is the criteria for this? Is the applied force needs to be bigger than the maximum static friction force. So what is the maximum static friction force? Well, this is mu s times the normal force. For applied force needs to be greater than or equal to static friction force. Our normal force, what is our normal force? Well, our normal force in this case, not always, but in this case, is equal to our gravitational force because because neither go up or down. So this would end up being 0.9 times 1,000. And so this should roughly be about 9,000 or so. I don't know the exact number. Let me punch it real quick. 8,820. Okay, so we need to apply a minimum of 8,820. Once we apply just over this, the refrigerator will stop moving. We'll start moving. When the refrigerator is moving, we look similar. Free body diagrams look similar, but our friction force is going to be smaller than our applied force. Because the kinetic friction force is always going to be smaller than our static friction force because it's easier to move it, to keep an object moving than it is to prevent it from moving. So what I'm going to do here is now I'm going to try to figure out what my acceleration is. And so in order to do that, I have to use Newton's second law, which is your net force is equal to your mass times acceleration. What is my net force? So in this case, I'm going to be working in the horizontal dimension here. I don't really need to figure out my net force in my y direction because it's 0. I'm not accelerating up or down. So my net force in the horizontal direction is my applied force minus my friction force. This is my mass times acceleration. So my applied force would be 8,820. My friction force is the coefficient of kinetic friction, it's normal force. This whole thing is equal to 1,000 times my acceleration. My coefficient of kinetic friction is 0.7. My normal force is 1,000 times 98. This whole thing is equal to 1,000 times 8. So 8,820 minus 8 divided by 1,000. So my acceleration should end up being 1.96 meters per second squared. Okay. So hopefully that gives you a sense of what to do. If you have any questions, just let me know. We have about 15 minutes left in class. So what I want you to do is I just want you to use your newfound knowledge. Just try to revise your explanation for the meter stick demonstration. When you finish that, you can use the rest of the time to work on the Newton's, the introduction assignment, the free body diagram, and the Newton's second law problems. So we can keep working on that. If you have any questions, just let me know. Be happy to answer them. Okay, so we got 1 minute left, so I'm gonna wrap up. Oh, we got 0 minutes left, so I'm gonna wrap up here. Thank you all for being so participative today. I was actually being observed, so that helps a lot. Anyways, in terms of your homework, the only homework you have is to keep working on the free body diagram introduction / unit second law thing. I set the due date for next Monday. I think what we'll do is I want you to try to do some of it over the weekend. On Monday, what we'll do is we'll keep working on it. If you have, so I want you to do as much as you can. On Monday, I'll try to, and I'll answer questions and stuff on Monday, and we'll have a little bit more time to work on it. So it's okay if you can't manage it, but I do want you to try to at least knock out some of the easier problems on it. And then on Monday, I'll try to answer any harder questions. Submit the graphic organizer if you haven't already. Try to wrap it up. If you aren't super sure of how to explain what's going on, right? I'm not grading it, so just give me your best shot for the exit ticket. I'm not grading it, so it's not a big deal. Just do your best. Other than that, that's it. I will see you all next Monday. Thank you all for being so great today, and have a nice weekend.
Thank you.
Thank you.
Have a good weekend.
Thank you.
See you around.
Thank you.
Bye.
Farewell. Bye-bye.
Thank you.
Was I right?
Thank you.
Yes, you were right. Yes.
Okay.
Yeah,
you.
exactly. Yes. As you go along here, basically the amount of mass that your hand the ruler has is increasing. So
Okay. Cool.
Yeah.
Thank you.
okay.